First of all, welcome. It's a great honor to host this first inControl podcast live show at ECC 24, the European Control Conference. I'm going to start with a thank you to the organizing team for inviting us and making this possible. The NCCR, of course, who have been supported, NCCR Automation, who has been supportive since the start of this journey, and Blackbox, those who are actually recording this episode. I'll just mention quickly, for some of you who may already know the podcast, it doesn't need an introduction, but those who don't, this is the first podcast on control theory. Our format is long interviews with renowned speakers, but also historical accounts, and as of today, live shows. So I hope we'll convince you to continue following or start following this show. Today we're going to have a panel discussion on the subject lessons from AI. What can we learn from the hype? So the goal is really that of doing some soul searching, if you wish, or discussing the raison d'etre of control in the face of these new developments in machine learning and AI. The session will be moderated by myself, Alberto Padoan. I'm with ETH Zurich. And our panelists are Munther Dahleh from MIT, Florian Dörfler from ETH Zurich, Rodolphe Sepulchre from KU Leuven and University of Cambridge, and Micheal Jordan from UC Berkeley. So in one way or another, you have already and will realistically influence the development of AI, machine learning, and control theory. So I would like to start with a twist on a quote by Marx. And the quote is the following. So a specter is haunting control. The specter is machine learning. So what I would like to discuss with you is starting from the facts. So the perception is that modern machine learning has arguably had a more tangible real-world impact in a few years than decades of control theory, and some perceive today control as a subdiscipline of machine learning. So what do you think machine learning, why do you think machine learning has had such an impact, and how should we how does this perception affect our field, and how should we react to it? I will give you, leave you the stage and hope that you will continue the conversation, but I will prompt you in case. Does anybody want to start?
I wanted to push back a little bit on this history. First of all, machine learning is not really a field. It's an activity. It's a problem-solving discipline. You pull things from optimization, from control, signal processing, economics, you name it. It's kind of a free-for-all. If you look at a textbook on it, it's a bunch of topics. There's a little clustering here, a little regression here, a little reinforcement here. It's a collection. So let's not think of it as a field. Let's think of it kind of as an activity in this era. Okay, AI is a buzzword. And so, it used to be we'd say just machine learning. That was kind of a good enough terminology to reflect the activity. Now you have to say AI and machine learning. When you introduced us, it was AI, machine learning, AI. And that was like Google, and that was the PR in Silicon Valley. The old AI idea of the 1950s didn't go anywhere. Still to this day, nothing new happened. Basically, machine learning scaled, gradient descent at scale, co-state equations from optimal control at scale. It's just the massive amounts of data that just can leak into every part of a problem. And you put that together with GPUs in the cloud, and the scalability is pretty impressive, and so it does really great things. The other quick comment is that applications-wise, I would push back. I mean, I think that, it depends on how you find these things, but think about supply chains. Think about finance, think about transportation. All around the world, it's changed all of our lives. It's just hidden. It's not in the newspapers. But it's there, and it's omnipresent, and it's critical that it was done really, really well. Now, more and more, that's machine learning. It's data. But it's control, too. It's model predictive control. It's planning. It's thinking over long stretches of time. It's adaptive, and so on. So trying to define, that's machine learning, this is not, the hype is here, I think is actually a losing proposition. The applications are vast of this kind of technology, data and feedback style algorithms at scale, done with the infrastructures that we have, and then with thinking humans guiding it. And when we get off to the envelope of the challenges, though, we should maybe talk more about those, because that has nothing to do with hype or whatever. Those are clear challenges, and we should talk about them.
Yeah, if I can just reinforce what Micheal is saying. for me, machine learning is a discipline, but it's sort of an emerging discipline. And every new discipline in engineering usually emerges from a new technology. So we have seen a new technology in the 90s, that this internet and this interconnection of everything and this generation of huge amount of data, and that led to new problems that created a new discipline. So control is also a discipline that emerged from another technology, and therefore it's not like control missed the boat. It's that just the control as a discipline is the outcome of another technology. And so every technology brings its new discipline. Doesn't mean that we need strict walls between the disciplines, but we also need to respect the time course of each discipline that rises and then at some point develops a proper theory. I see what you are saying is that we still don't have a proper theory in machine learning, but it's coming.
I didn't say
right?
that. I don't think that's true. We have plenty of theories, and there are good ones, and upper, lower bounds of
but
all
you
kinds.
refer this morning to a discipline that however we
No,
call it.
This morning I don't take too much time here, but think about chemical engineering. It took 20 years, and in the beginning there were some theories. They just were a little not adequate to the full scope.
Yeah.
And at the end there were some theories, and it evolved.
Yeah.
But it was guided by theory throughout, and same thing with electrical engineering. And so I think right now we have tons of theories. There are amazing optimization theories, uncertainty quantification, you name it. And some of them are effective in guiding us, and some of them are going to be left on the side. But it's all very much guided by theory.
I think there's an important quantifier here, namely that is control theory versus control engineering.
Mm-hmm.
As you guys rightfully said, theory itself probably had little impact, but the engineering side has a lot to the state, right? And maybe the more precise question we should ask: why does control theory itself has so little impact these days on modern developments, right?
Mm-hmm.
If I give my own answers, I think partially because as a theoretician, you're also a bit elitist, inward looking at your peers and not looking at the problems in the outside world, right?
Mm-hmm.
So that's definitely contributing to that. Whereas an engineer would be less constrained by formalities, less by rigor, embracing more empirical side, and having more computational mindset, which theorists don't have typically. And that's, I guess, the interplay.
Munther?
Well, I'm not going to make a distinction between theory and applied, because I think control theory has actually had tremendous. So let me just say the discipline conversation is a complicated one. Control system design and control theory was predicated on areas like decision theory, which is optimization and game theory, statistical learning and information theory, and algorithms. And this is together allowed us to figure out how to deal with decisions under uncertainty in a dynamically changing environment. That was sort of the core discipline of our field. I think we are not as strong algorithmically, I would say. I would say maybe computer scientists are a lot stronger and so forth. But I think in terms of the interaction between information and control and decision, I think that that's part of the strength of this particular field. So I think this question that, AI, the buzzword, which really includes all algorithmic solutions plus all learning solutions, which I think I agree with Mike on that one, has stolen our lunch and we're now left behind and so forth. I think that's not the right way to think about the problem. It's that the controls as a discipline and as a combination of things has a lot to offer and has a lot to learn. There is a wave of technology that is moving very, very quickly, and it's moving with us or without us. And the question is, how do we position ourselves to help in the development of that technology? And this is where I would say the question, because it's moving fast, we have to move fast, and we have to potentially not sort of abandon the theory, but understand what theory is needed that can help this particular area. And I want to emphasize that much of what when you say applications, chemical engineering, we have rockets that went to space, and we have planes that fly. These are all based on robust control theory and understanding the uncertainty and how to manage the uncertainty and so forth. Those are great applications, and yes, they've taken many, many years. It's taken 75 years to get to ChatGPT. It didn't just happen yesterday. So again, the historical context have to be put in the right place. So I think the questions have to be phrased, how can we be running with this technological revolution?
So this connects also to what Rodolphe just mentioned. So should this be the technology that we envision as being the enabling technology for the formation of a new field, as you were alluding this morning in your plenary, Micheal?
I don't think it's technology. I mean, it's gradient descent. That goes back to like 1850. You know, literally, the transformer architecture is kind of an interesting architecture. It puts together the pieces in a continuous way. I think that a lot of engineering fields is about how do you put together the pieces, like modules, and what are the right modules. And I think that's probably where we're not there. And I don't think that's so much a theoretical question as kind of a figure it out kind of question. You know, it took a while for, you know, you take Maxwell's equations, there was no kind of modules, right? You had to kind of figure out that I'm going to have an impedance here, and you know, I'm going to put together things so that I can, you know, flip things in and out. And we don't have that so much. But you know, the computer scientists really aren't the ones who thought about most of this. They built the pipes that could bring the data around. That's really all they did. Algorithmically, not much sophistication. The algorithm is all optimization theory, and increasingly equilibrium. Now, you know, there's exceptions, and I guess I got a little bit of a sigh here from someone.
No, I think
Let's
when you
give the word
say
to Rodolphe.
gradient system, it's only gradient system. I think it's an oversimplification, because then you can say it's engineering since Euler has always been gradient descent or least square. And you pointed this morning very, very clearly what's the novel component, what's the novel question in the area of optimization, which is to deal with huge amount of data. And this is really what makes the problem novel. And I would say that control theory was not developed to tackle this problem. And if control theory has one thing to learn from statistical learning, is how to incorporate statistics in representations of signals and systems and learning. So, you know, I think we should, it's good to acknowledge that in the end we all try to do the same thing, which is gradient descent. But it's also, I think, useful to identify what is novel, where is the fact that control is not prepared to answer those questions. I think we have to acknowledge that it's not having a bad look at control. It's just acknowledging that control theory was developed at a time where that was not the main question. The main question was how to deal with feedback. And this question still exists. So perhaps this is where control can contribute to machine learning and to this new discipline. But there is also another element, which is how do you cope with huge amount of data? And this is where I think
that's the feed-forward side of control, right?
Exactly.
And it's just the part that not as much potential was paid, because
Absolutely.
you could get away with, you know, if the feedback was good enough, you didn't have to keep the model updated,
Absolutely.
just continue to adjust. And so it worked for a long time and lots of problems. And now, you know, ChatGPT doesn't necessarily solve a problem, right? It's not really, I would even call it a technology. It's an artifact. And yeah, the technology is, you know, I don't want to diminish it too much, but it's literally gradient descent, you know, on big primary systems with GPUs, so you could do heavy, big scale matrix stuff. And then it really is all the data. And I think that's probably where we're going to agree that control theory didn't say, let's embrace all the data. You know, model predictive control was a big success of control theory, really, in chemical engineering. But, you know, the control theorists didn't say, let's study model predictive control. It was all about feedback control. And so I think that was maybe what was missed. But it's not missed forever. It's now the opportunity is to put together, okay, we're going to make a really good model, update it, keep it going, and in the context of feedback and then robustness and then multiple actors and, you know, et cetera, et cetera. So I wouldn't so much call it a technology, it's a thinking style that's emerged on top of this, you know, the cloud and the GPUs and what the pipes that the computer scientists gave us.
You know, I heard the same discussion from people in the late 70s, early 80s when NPC came up. You know, control theorists thought of that as a very ad hoc solution. If you're not good enough, you call it the computer. It seems like we have the same discussion now again.
Yeah.
But we accepted the NPC. And now the question is data ad hoc or not.
Is data ad hoc? Is that a question?
Yeah.
Seriously?
Well, ask around the room.
Well, we should ask, because I mean, it's data ad hoc. I'm a statistician. I'm going to have real trouble if you say that to me the data is ad hoc.
Yeah.
Well, I want to add that I think of AI, the buzzword, as a new engineering field, and it's, you know, it pulls from everywhere, you know, and so I think it's not important. It is important to think back and say, did we miss the opportunity here or there? But there is a new engineering field, and it has architecture, it has interconnections, it has questions about data, it has questions about robustness, and a lot of these tools and ideas that control theory has contributed to and has a lot to add. We're not going to be everything. There's going to be a lot of people involved in this engineering discipline or engineering field, actually. So we play our role, or you can expand your role, right? And so I would say it's very important to understand interconnections if you understand deployment of AI systems. You have to understand how uncertainty propagates, how, by the way, a lot of data and very little data in situations that matters, right? And so we are also in the small data regime, not in the large data regime. And so thinking about that, which is also an area of systemic failures and systemic risk and small data sets and so forth. Again, this is just an area where people have a lot of expertise and tools and can jump in. The question is to pick the right problems and to think about the right abstractions. I really believe that we have to continue to contribute in that abstraction world. There will be others that are writing the hacks, and then they can probably use some of the abstractions to help them in the hack. We don't all have to do the same thing. We don't all have to be OpenAI developing large language models. We have to play the role that we play in. And so in this engineering field, I think we have a really important place to play.
It's wonderful. So you've touched already on possibly all of the keywords that I have here.
Oh, so
some of which are the role of data. Another one is architecture. So how to design actually an architecture from scratch. This is something that I've discussed at length also with John Doyle in one of the previous podcasts. I don't know whether I should pick up on one of these and explore them further, or actually stir you more and create a bit more controversy. But I think I'll follow the second. For this specific episode, I resurrected a quote that I like very much from the first Bodhi lecture from Gunther Stein, 1989. So in that lecture, Carl Ostrom says that the lecture is like really good wine. It ages superbly. So Stein identifies two trends in control theory at the time. So one is applications are starting to include things that are more and more dangerous. And we may argue that this is the case also for machine learning systems. The second trend is an increasing worship of abstract mathematical results in control at the expense of more specific examinations of their practical physical consequences. So I'm curious about how do you feel about these two trends, whether they're still present, whether they're not there, and how do they relate also to this machine learning hype?
I just want to really object to this idea that that there was a theory and then there was an applied. It's not true. I mean, all the applications started from some major theoretical development. I mean, the whole idea of system theory, that how it came to bear, and our understanding of robustness, our understanding of design, came from theory. And of course, then you have to take it and you deploy it, and you have to do a lot when you deploy it. But it's not a game. It's not a fight. Sorry.
I also would like to object to this distinction and say the opposite of what Munther just said, namely that every theory emerges from an application in engineering.
And don't disagree.
If we drew a diagram, it would have a closed
have a closed
theory
feedback.
application.
I don't disagree with that. I don't disagree.
So I would
with
say
that.
that if I look today at all the important pieces of theory of control, I can link them, each of them, to a specific technological problem. And I think that perhaps now, I also shared when I was so in the late 90s, I felt like, okay, we are just turning into circles, we are just writing theoretical papers. That's not what I was looking in the field. And I started looking in other fields, and then going to conference in machine learning, going to conference in neuroscience. And I've seen that this is in every single community. Every single community faces the fact that it's hard to address new questions. It takes time, and you need to write your paper. And so we are also in that sort of productivity cycle that sort of pushes us, and more so, unfortunately, to get stuck in our little niche just because this is where it's easy to write the next paper. So I think that if there is a conflict between theory and practice, it's more like we don't hear enough questions and we hear too much about answers. And so it's always a sort of an effort to go back to the questions, and is this really meaningful for what is needed? So if there is a conflict, I would phrase a conflict in terms of questions and answers, or questions and methodologies rather than theory and practice.
It's wonderful. Any comment
Can I
on your
pick
side?
up?
Yes.
Well, I can comment, but I want to pick up on your question, which is the Gunther Stein lecture, Respect the Unstable. I somewhat hate it when I'm in the room with reinforcement learning people and they say, oh, the role of control is a safety critical system. I feel like we shouldn't be pushed into that niche because we have so much more to offer than constraint satisfaction and stability. Of course, we can do that and we're good at that, but we have many more things to offer, as Munther said, like thinking in architectures and block diagrams, the power of abstraction. It's not just the stability and safety problem.
And I want to emphasize that I think, coming from my recent stint of launching IDSS, which is Data Systems and Society, the role of all of this to society is really important, and understanding economic and social systems and how decision theory is interacting with economic and social systems. So we have to broaden a little bit. And this cannot just be on the fringe. It has to be part of our thinking of how we impact social systems. I mean, my colleague Jeff Shamma keeps reminding me of the fact that one day there will be all sorts of agents that are trained somehow to do something by reinforcement, policy iteration and the next policy all the time. And these things are interacting with us, and we're adapting to them, and they're adapting to us. Not necessarily intelligence, but these are systems that will be rolling, and interacting with us. And I don't know where the social system will converge to, what equilibrium we will be operating at, and what disasters we will be creating by having these reinforcement systems sort of sitting around and interacting with us. I think it requires us to take some time and think about some abstractions to understand what is the outcome of many of these things and anticipate before they happen. So I think we gotta think about this. And economic systems is the same thing. I mean, I always tell people, what is the difference between Amazon and a country? Well, it doesn't have currency, but other than that, it's
going to have currency soon.
I think they have currency soon. So we are dealing with massive economic systems based on these types of, call it technology, call it development, call it engineering, and it's decisions, and there's a lot of decision theory, and our community could engage really excellent conversations about the role we play in thinking about these types of systems.
Another one is, so there's other disciplines that we haven't talked about that much here, but statistics comes up from time to time. Statistics had the same problem. They solved some big problems back in the 30s and 40s, quality control, medicine. The FDA arose out of, making sure that the good drugs went to market. And out of those successes came yet more abstract theory. And so for a while, that was it. But that was okay, because that kind of taught people to think, how to take that kind of style, make a stylized version of the problem, and then solve that. And now you know how to go off and do that. Still, statistics is very much alive, and it is embracing the big data era. But it still hasn't resolved the Bayesian frequentist dilemma. And so that's a dilemma really more for a practitioner. When I go into a problem, I got to write a piece of software. It'll be used over and over again by whoever out there. That's more frequentist. It should work on a frequency basis. Or am I going to get my feet in and work with the data, really work with an expert? That's more Bayesian. And so it's kind of a working style. And you wouldn't kind of pick one and here's the mega theorem of all time. You'd say, here's some different kinds of ways of thinking about problems involving, in this case, in fact, uncertainty. Economics. So what I do is I move between fields. I still haven't done yet computer scientists, because I didn't find that much excitement there. But I did control theory, and then I moved into statistics. I felt that was a discipline where all this big data is going to be coming. Gaussian error bars are not enough. The bootstrap is not enough. There's got to be new kinds of uncertainty management. We kind of have it now. It's conformal methods. Conformal turns out to be closely related to control theory. It's tracking. Okay. But then statistics sort of seem to also kind of slow down and, here's what we know how to do. And reinforcement learning came, and everyone said that was the big new thing. I would just want to say I don't think that's true. I think that the big successes are these ChatGPT, big gradient descent sort of things. The reinforcement learning is just optimal control in a sampled style. It's a big search problem, and you could do it with large, brute force search with large numbers of computers with a well-defined game. You can do things like, AlphaGo. But I don't think that's where the success. That's really just control theory, and there's still a interplay going on between those two. But anyway, lastly, it's economics. So I think economics right now to me is the most exciting, poised to do the new things. Because economics is about definitely decision theory. Wald was the developer, but it's about mechanism design, which is control, and it's about when you bring together, it's social in the sense of I got many interacting agents, and some of them are computers and some of them are people. And there's now not 5 of them or 10 of them like in robots, there's 100 million of them, right? And they're all interacting through data and uncertainty quantification, and they're all kind of signaling signals to each other. They're trying to figure out things. And the economists who studied all that back in the 50s, as Arrow and others, turned it into something useful in that era. Then it got very stylized. It became just let's study auctions. Auctions. The big data wave finally started to arrive. There was a Nobel Prize the past 2 years for big data stuff in economics. But most economists were not ready for it. They didn't want it to come. They had their problems. But now they're also doing soul searching. But I think that they're ready to do what Munther is sort of saying, is to take the social point of view, because that's what they study. Social means really strategic agents. Okay, and privacy is something that is a social good, but I want privacy because I'm getting something for return. If I lose a little privacy, I get something in return. It's an economic concept. Fairness, economic concept, et cetera, all of these concepts. So I think that's really where it's going to be exciting, the kind of control meets economics. It was done in the 50s. The HJB equations, Arrow, et cetera, Kalman, all together. It all split apart. You guys, the young people in the room here, are going to help refurbish that within the context of all this large amounts of data.
And if I just follow up, sorry, out of
Definitely,
order,
please.
to say that, in fact, I think this is exactly the point I was trying to make. And I think we are very good in control theory in information design. Where do we allocate information to get the best decision? And how do you even design an information structure for a game and so forth? But there is another layer here, which is the incentive design and the elicitation aspect, so that I understand your hidden motive and you understand my hidden motive, and we can now cooperate and work together. This is an area where, yes, economists have actually started and thought about the whole mechanism design and auction, but none of that is done in a dynamic environment, and none of that is done in a situation where things are changing rapidly. And by the way, I want to say another thing that is important. Why do I say dynamic? Why is that important? Because we're not going to exist in equilibria. I think this stationary story is going to go away very quickly, and a lot of transient non-stationarity is going to be in place, and understanding the dynamics becomes critical. So in that field, we have to do it in a dynamic setting. In many agents interacting for social systems, we're going to do it in a dynamic setting. So we're going to bring in dynamics. We have experts in dynamics. We have to adapt those kind of expertise to the problems at hand so the problem doesn't grow very rapidly. And we often talk about interconnections, and interconnections, what do we talk about when we talk about interconnections? We talk about local properties that can propagate and remain as a global property. What are the local properties that we can think about? We think about interconnections in a systematic way, back to your architecture question. So, but we have to bring in the right questions in the right applications. We have we are thinking about these tools. So the opportunities are huge, right? But requires some bifurcation from where we are now, because some of our models aren't the right models for these problems. And
so economists have iterated games, as you know well, and iterated games are dynamics, but they made it so sterile.
yes.
It's the most sterile topic. So if you're a young person, you say, I should study iterated games. It has these agents and they're doing over dynamics, and it's not just about the Nash equilibria and so on. You read it, it seems completely sterile. You're pushed away from that. I would go in exactly the opposite direction. Throw out the textbook and start it over again. Start it over again, because it's exactly the right kind of problem to wait. And what Munther said, I totally agree with. It's all about the non-equilibrium. You got 100 million actors, acting. It's all going to be about the evolving equilibrium. Are they good ones? And how do you get the information that you need in a world like that? Humans, I think, when you talk about AI, we're starting to mimic how humans, play chess, or how they, learn calculus. That's not where our intelligence is. Our intelligence is dealing with each other and with the complicated, uncertain world all around us, and mitigating uncertainty by communicating, and also being strategic about what you learn from other people and what you tell people and how you interact. That's what humans evolved to do extremely well. And I think that our system science is the only hope for these computers. It's not going to be take out a human and put in a computer and it solves the world's problems. The naivete in Silicon Valley and in computer science departments is breathtaking. Let's build super intelligence. And we didn't even say this stupid phrase AGI, but that's going to solve the world's problems. The naivete is breathtaking. So you guys, young people in the room, you're in system science now. Don't even use buzzwords like that. Think about what is the overall big system.
Unless you want to get a job.
That's a very strategic comment.
Yeah, talking about the hype, which is part of this the podcast team, I think we should address the bandwagon issue. When Shannon wrote this paper in 1952, I guess, he sort of signed the end of cybernetics. So in this hype, somehow, the bandwagon was clearly announcing the end of the hype. And my reading of the hype is that it's announcing the end of something. And I certainly would not want to think of control as being just AI, if we use AI in this very broad sense. Because I think that control, for me, of course it's interconnection, but control is so broad because of its abstractions. But I think there is something, for me, that is very unique in control that I do not find in the sort of discussion that we are having, even if it's a very important topic, but it's interconnection as physical interaction. So this sort of embodied intelligence. And I find that we have very, very pressing questions in the field. You know, it's sustainability, climate change, health, biological control, quantum control. All of those are, the central questions there are, how do you interact with physics? And I think this is a sort of a brand where control has something unique to offer. That it's not just algorithmics, and maybe it's not algorithmics enough, but it's also physical and physics-based.
But what about AlphaFold? That wasn't done by control theorists.
That's a very good point.
And that's probably the biggest breakthrough in the last 10 years in
Yes.
kind of physics-oriented learning.
Yes, but I think it's a wonderful example, because this is an example of where this approach of machine learning does work. But in my opinion, it doesn't explain the brain, and will never explain the brain. And I think
But why do we have to explain the brain?
No. One area where I think machine learning so far has not delivered at all is neuroscience. Okay.
I totally agree, but why should we talk about the brain? I mean, what we were talking about is we don't want to take out a human and put in a computer that replaces a human. If we understood the brain, we could do that. We could make a bot. Why would we want to do that?
I think that the brain is one very, very important question of the time, just for health. And for you know,
that's a difference. For understanding Alzheimer's disease, I'm totally on board. I'm not ready to get
that's
it.
what I'm talking about.
Sure.
So using
but
control system,
that's not understanding the brain. Understanding the brain is Wiener, and it's like how does information flow?
It's not at all in that sense that I was.
Okay, well then
I'm talking about the engineering question. How do you interact with the brain to save Parkinson, to help patients? And we see a lot of technology being developed.
Those are medical issues. I'm on board. But the body is we work on it. But the brain as a medical entity is different from the intelligent system up in my head that we need to study and understand it. And maybe the people get that, but I think that's an important distinction to make. I resent the fact that everyone said we discovered how the brain worked. That led to neural networks, which led to all this technology.
No.
You're not saying that.
I'm not saying
that.
But
every newspaper says that.
Yeah.
Neural-inspired computing,
What I'm saying is that, we just finished the flagship project of 1 billion in Europe of 10 years. And it's now considered to be a total failure. I think and a book is going to come out about this. But the fundamental explanation about that is that it was thought or announced that these big data would solve.
It's top-down science.
Yeah.
It's some bureaucrat in Brussels decided this is what we're going to do.
Well, I think it's much more than that. And I think a lot of scientists fall in that trap as well.
Yeah.
And I think that a value of control is that, we see that I think we a lot of progress in quantum will come from control. A lot of progress in medicine of the brain and biological control will come from control. And this is areas where data will not be enough, if at least, okay.
But again, let's go back to AlphaFold. I really think that's a critical thing to hear. AlphaFold it would not work if they had put physical principles in it.
Absolutely.
Okay? It would not have worked.
Absolutely.
So, and there's no control theorist in sight. So I want to be clear on, yes, I do think control has something to give, but I don't think it's that. I don't think it's uniquely that control theorists have physics. because I think that most other fields or working with machine learning are not doing control theoretic approaches. I want to see specifically what it is about. Control to me is about uncertainty management and robustness and interacting when you don't have knowledge, when you have limited knowledge.
The difference between AlphaFold and curing Parkinson's disease is that there is enormous variability in the physiology of the brain that you don't find in the unfolding of a protein. So when you can reduce something to pure physical laws, fine. I think the main question why we are making so little progress in fields like quantum control or biological control is the uncertainty. And there is a level of uncertainty there that will never be resolved by data. That's at least what I think. And this is a fundamental issue that has driven the control discipline. And I would say, just to finish, because you were saying that interconnections, it's all about interconnections in the end. But I would say that control theory today has no theory, not the beginning of a theory, to cope with heterogeneity.
True. Correct.
And I think that it's fundamental to tackle any problems in biology, to develop new concepts and new theories that will tackle uncertainty, but at the same time will show the value of heterogeneity. And so far in control, we have always considered that heterogeneity is the enemy that we have to fight, and we have to make everything homogeneous. In fact, engineering has very much worked that way. As long as we work that way, we will not make any significant progress in important problems. And I would think that climate change also involves a lot of variability and uncertainty that will also require these better methods to handle heterogeneity.
Just want to quickly respond because I mean I think
I'm not convinced by this story. Yes, heterogeneity is economics talks about heterogeneity all the time. It's never about how homogeneous it is.
They always talk about heterogeneity and their models are homogeneous.
No.
I'm just saying,
econometrician's model is not homogeneous.
No. I'm talking about theory, right? You're right. And no, just say that these are a lot of points that you raised, and it is true that there are systems, that we're getting to a limit where I don't know if data would not be able to help in quantum systems or not, but so far it hasn't.
I didn't say it would not help.
Okay, all right. But I would say those are not the only applications for control theory. I will go back to your cybernetics, and I would say that, yes, maybe Shannon information theory sort of put a stop to that thinking, but I think it's coming back. And I do think we are in cybernetics 2.0, where now data and statistics are added to the additional components of cybernetics. And I think I think the applications are very broad, and as I said, engineering around the buzzword AI is happening, and that's the role we can play. We can also play in quantum control. We can also do the nuclear fusion. We can also go play in those roles. But there are many other things that are moving that are social and economic, right? And they're not safety critical, but can become safety critical in a different way, right? And I think it's, and yes, I agree that heterogeneity is going to be a big part of it, and we have to advance our technology and our ability to process and think about heterogeneous systems interacting and so forth. I agree with that 100%. But I don't think we should exclude this sort of what you refer to as non-physical systems to focus only on physical systems. I don't think decision theory is.
I didn't say that.
I didn't say only. I didn't say only. I said also.
But you said the word uniquely, and I just wanted. That's where I'm pushing.
That's what I meant.
It's not unique to control.
Well,
lots of other fields do physical systems meets data. That's just. Half of my campus
is the feedback loop between the physics and the algorithms.
Yeah, a lot of them do that too. The people are designing chemical, new chemistry. It's all about that.
I'll jump in.
And it's informed by Lyapunov functions. So if you think that Lyapunov is control theory, then I agree. Control theory is everything. But
one last comment from Rodolphe, and then I'll jump.
Yes.
There's just
is this enough controversy, by the way, or you want
That's great. That's great. Keep going.
There's one thing that I wanted to quote about cybernetics. It's the definition that Wiener used to define cybernetics. He said, the science of control and communication, whether in the machine or in the animal.
Exactly.
And this is what Shannon put an end to. He said, no. Also Turing said, this is too difficult. Let's separate the animal and the machine and develop a pure machine program. I agree that we are coming to cybernetics 2.0, going back to looking for a language and a theory that can, whether in the machine or in
the one thing that I think that Wiener got wrong, he did have this big overarching, but he wasn't enough of an economist. And so he had von Neumann sitting there. I think their personalities were too strong. They hated each other.
Yeah.
And they all hated Wiener, just to say. Wiener he was fascinated by, a squirrel, so he led towards robotics as the main application for the field. Robotics is great, absolutely, but it is limited. It is limited. And
but
the economics perspective says, no, I'm going to solve control problems involving multiple people interacting with strategic things and uncertainty and robustness and a market design. So Arrow was in that same world, Ken Arrow. So it's, and Stanford, they all were interacting, David Blackwell. And I do think it was very helpful that someone said, let's break it apart. It's too complicated. That was important. I think that was critically important. It's exactly the opposite right now.
Exactly.
Because it's complicated, you got to put it all back together.
Yes.
And it might be that economics today is the best answer to how to
Cybernetics 2.0, I just want to say everything that, plus let's really make sure the incentives are there and the multi-agent and the decentralized, prices take the role of, the communication structure. It's partly because there's prices. All that has got to be in our big systems. Otherwise, it's just a top-down design of something that's not going to work.
First of all, I'm super happy of all the problems you have outlined so far. It's great. I want to add one more, and that's energy. These days, also related to the AI hype, it's not unusual to hear that we want to build small nuclear reactors next to data centers, which is obviously, at least to me, a bit crazy. So I want to take a step back and say, okay, given the fact that we are very good at leveraging abstraction, we are very good at dealing with interconnection and feedback, we know fundamental limitations of systems, or at least we're familiar with the concept, what can we give back? So in terms of methodologies, techniques, ways of thinking, what are your thoughts?
You mean in the context of energy or general?
Oh, no. In the context of all the problems that you've mentioned until now.
But you said energy. Why did you say energy?
Yeah.
I just wanted to add one more problem to the bucket list.
The energy is coming from Sam Altman. So and just to push, it's OpenAI, which says we did this great thing with 100 billion parameters. If you give us 1 trillion, we will solve all the world's problems. He wants to build a tower where humans give queries to the tower, and the tower gives back answers and solves the problem. And so he is spending all of his time going up and down the West Coast trying to find energy sources and nuclear reactors and all that. It's this wildly fanciful, out of control, non-engineering perspective on the world.
That
we need energy. Sorry, please.
A single-digit percentage point of the world's electricity is used for data centers.
Yeah.
It keeps on climbing steeply.
Yeah.
What's the percentage?
I forgot the exact number, but something like 3%.
Yeah. So I have a suspicion that ChatGPT is kind of going to, top out. You can't. It's doing amazing things, but there's not more data for it to ingest at some point. And the idea that one group of people would hold all of that and then run these even more massive models, I think that's going to go away. You're going to have these more verticals where you solve problems in a context. And then someone ran some big model long ago that did kind of the basic language stuff. And then you add a vertical on top of that. You're not going to need the massive, Sam Altman style. Now, you need energy, however, and so I would like to hear about what you have to say about nuclear reactors and all that. But let's just say I don't think this Sam Altman thing is at all calibrated to reality. I think maybe it's true, but it's not clear.
There's been a corruption, I think, with what happened with large language models that, of course, companies will do whatever companies do, and we have no control. But then this attitude within academic institutions that we got to be training people to think about large language models and how to use them and how to create them and I think we need to be training people on fundamentals. We got to train people how to think about problems and how to formulate a problem and how to solve a problem and so and I am bothered a little bit that even at MIT there are very few people who take actually advanced control theory these days. It's just not a popular class. And they take dynamic programming in the context of reinforcement learning. But actually, the number of people that understand even linear system theory has shrunk. Now, linear system theory is important not because everything is linear, but because it gives you a cohesive intellectual framework to think about problems, how to formulate them, how to solve them. It's a great pedagogical education. So what are the problems? I think we also got to start thinking about causality. I told you I'm going to have to talk about causality. Got to talk about causality. You know, you've got massive amount of data, and you need to understand. You need to understand the difference between a probabilistic model and a causal model, and where your experimentation has to be done to create the causal model, and what can you use with synthetic controls and that kind of stuff. We need to educate and expand the knowledge. I also want to say that the role of statistics in control theory has to become a lot stronger. I agree with what you said, Mike, and I also think that high-dimensional statistics has been a revolution in statistics, right? And I think causality has to come into the picture as well from a statistical point of view, and we have to put them all together.
I'm glad you rose causality, because I was earlier going to say x dot is equal to f of x comma u, right? We all love that equation. What is u? Well, use the thing that causes something to change.
Yeah.
Right? If you put something in your model that doesn't actually have an effect on x dot, it's useless. Well, how do you know a priori what u is?
Yes.
Well, for a robot, I know. You know, I put the oil in, and out comes the movement.
Yeah.
But for huge numbers of systems, you don't know. So what do? Well, you do causal inference.
Right, exactly.
And causal inference is statistical. The econometricians kind of borrowed it, but it's Neyman and Rubin and others in statistics. And there's, as you know, synthetic controls is one amazingly interesting technique for it. But exactly, control theorists who don't know about causal inference, or the whole point is you're doing control. You got to know what the control variable is. That's the first starting point. How do you know the control? Well, if you have a lot of data,
exactly. So
you can start to figure out what the control variable is.
This is a bifurcation from physical systems. Physical systems, we understood that we cause and effect, and we did that, and we wrote the models exactly that way, and we understood what causality meant. But in these large data sets, well, unless someone has to dig out and understand the physics, most of the time I don't have this information. And just because I have a probabilistic model does not mean I have a causal model. And that people make that mistake all the time, you know.
New York Times makes that mistake
all the time, you know. And I think that we have to, so when you say what problems, I think we got to take those problems into our curriculum and make sure that all of our students are there with the high dimensions, with the causality, with the heterogeneous systems, right? We need to kind of like upgrade where we are if we want to play in this game, because the game is moving fast. The types of models are different. We gotta rely on data, and we can't just rely on physics. I wasn't saying you just said that only thing is physics, but I think not because these systems are not coming from physics, but because the data is not explained. The data is just sitting there, and now you have to start processing, and you have to start.
I'd be a little worried if the first control class is all about, F equals ma. That's not gonna attract the younger generation.
Actually, I think data and statistics are sort of secondary effects. There's something more important that in education we have to work on, which is bringing people faster to computational methods. Because I remember my own curriculum was like pen and paper, 20 courses.
Yeah.
And then only in the PhD I figured out, there's computational methods that also have a theory. You can do theory with them. They work in practice. But somehow that is not taught, or not taught early enough.
So Alberto, at least it seems that there is an agreement among all of us.
Even though we agreed to disagree earlier.
That we should throw away x dot equals f of x. That's
maybe,
the one
maybe,
thing we would
Maybe.
Well, not throw away as much as put things in the right context. I think, I like to teach linear system theory, and I keep reminding people I'm not teaching it because that is the end point, but that's the starting point. And I love the examples that we can actually show cascaded effects. We show small perturbations become large perturbation. We show that linear systems with large matrices can look like turbulence, I mean, all of this stuff is really critical to understand what you're dealing with. But of course, then the research has got to go to the next level. It's got to advance to the next level. So your question about where to go, there's many areas. So the question is, how do we do this? How do we connect ourselves to understand what are the problems that need to be solved? How do we actually bring that into the community? To me, that's an interesting question, right?
So I helped design a data science class about 10 years ago that became super successful. I don't want to brag too much, but it was for freshmen, and it made no calculus requirements, but it was about statistical data analysis. And so it said, here's an example of a problem. I got 2 columns of numbers. These are people with a treatment. These are people with a control. And the numbers obviously differ in various ways. Are they really different statistically? Can you quantify that in some sense? And you could now, if you're a statistics person, you would start designing t-tests, and you would start to give asymptotic arguments about normality, and you would start going down that whole path that takes 5 years for someone to not really quite understand. Okay. Instead, you can do what's called a permutation test, which you say, well, if they're actually coming from the same distribution, I can put them into one big long column. Okay, I just make the exchangeability assumption that the ordering doesn't matter. Put them in one column, scramble them, doesn't change the distribution, split them into two again, and calculate my statistics. Do that over and over again, and then see where my original statistic was in that sampling distribution. So I just explained a permutation test to you, but you may have gotten it or you may have already known it. But the amazing thing is that a freshman who had no math understands that. And now the cool thing is that you say, well, let's program this up in Python. They say, what's Python? And you say, well, here's enough concepts to kind of do a random list, to do a random permutation, to make a histogram, and to put a number there. They do that, and they say, now go run off and solve your own problem. You got some data about like water usage in this place versus water usage over here. Is this different from this? They got super excited. It became the fastest growing class in the history of Berkeley. It's now being taken by nearly 2,000 people a year. And this is these young people that are saying, wow, this empowered me to think computationally, but I didn't have to go off and take a huge number of programming classes. It allowed me to do statistics, but I didn't have to learn about Gaussians and asymptotics. I just learned about permutations. And it's allowed me to solve a real-world problem in the context of decision-making. It was all about decision-making. And then that's 2 weeks, and then you do another little nugget. And I kind of think that's the way to go. And I agree with you. The linear systems are throughout that. So we kept it with linear systems, and there was the bootstrap with linear systems, and so on and so forth, but introduce these concepts. And I'm pretty proud of, 4 years later, you come out, you're ready to go out in the real world and solve actual problems. You can't write papers, but you can solve problems.
Wonderful. I'll jump in again. I have 2 comments. So one is you're anticipating already how. How do we change ourselves, or do we change the field? How do we do that through, for example, education or other means? I'm thinking, are there things that we can take inspiration from, let's say, our neighboring cousins, say, the way they change reviews, for example, the use of data sets and benchmarks. And the other comment I have relates again to the principles that I didn't manage to extract from you. So what could be useful out there in our neighboring fields that we can bring? And this connects again to the quote from the lecture of Gunther Stein, which ends this way. He says, we must place renewed emphasis on stating and teaching the principles of our subject clearly and well. The applications out there are simply too serious for us to hide from responsibility under a cloak of mathematics. So I wonder, how do you feel about these 2 comments I had?
Well, one thing I wanted to say quickly, kind of tangential but related. So the idea of how and bringing in concepts from different fields and so forth. There was a time, as you both alluded, where control was big in application, and then we developed, H infinity, L1, robust control, and so forth. We became actually too focused on the theorem and not on the next level, which was, this compression happened to us. And then there was actually sort of an expansion where many of us went into different fields, and people went to biology, and people went, I became more interested in economics and social sciences and so forth, right? But now what we need is to bring some of that back, right? And bring the conceptual questions back to the broader community in a systematic way that we describe to our community the challenges that we're facing in those different applications. I spent the last 7 months at the Broad Institute at MIT. This is the Genomics Institute. And I learned so much about really interesting control problems that are not in the realm of the kinds of questions we ask. I mean, one of the things I just kind of like I throw one in there and say, of course, they're very interested in sort of mapping a cell type to another cell type, and you do that through transcription, right? And so one of the interesting things about these things is that the measurements you make are unpaired. That is, when you measure something, you kill it. So if you measure a cell, then it's dead. Then you apply it to a distribution and you measure it in the other sides, it's dead. So you don't have this data set of x1, u1 equals y1. You have a bunch of x's, you have a bunch of y's, and you have a bunch of u's. That's a control problem of unpaired data sets. And there's a lot of interesting ideas about optimal transport and how to map distributions and all of that stuff, which, again, it would be amazing that we bring that kind of set of questions to the control community and say, if you want to think about theory, there's a whole bunch of problems for you to think about. And they're very interesting, and there are people ready to roll out this as an application. They're ready for you. They just kind of tell them exactly how to do this. So I want to say that, mechanisms within our community to bring back those people who went and done an amazing job elsewhere in different fields, bring them back in a systematic way. I would propose that as one idea for our society to educate us all.
I think what Munther is describing is the dynamics of any discipline.
Yeah.
And I think we have to acknowledge that dynamics and to somehow respect the dynamics. I don't think we can do much to force that dynamics otherwise. And I think it's a very healthy dynamics that, things grow and then decline. And it's because it's declined that people go out and look for new questions and those new questions. And so there is a sort of a evolutionary principle that is very healthy there, and I think we have to respect that and accept also that at some points the field becomes too diverse and branch out into other fields, and that's how new fields are started. So I think that the strength of control is that this dynamics is happening also because of the core mathematical training. So I agree with your example of the data science class, but I don't think it implicates that we should give up with the mathematical training.
I never said that. Just to be clear, I would never say that.
So
I'd say you don't start with the calculus,
exactly, yeah,
and then do everything.
Yeah.
You build up.
So it's a balance that I think we need to acknowledge that it is the strong core mathematical training of control that makes it so easy for control theories to branch out. But the danger is to get stuck into a sort of comfort zone. Yeah.
Let me add on that, on your question, what we can learn from each other. So I often find myself in meetings co-supervising students with machine learning people. And we often find each other on opposite spectrums, the one that you said, so sort of going for math, pen and paper, versus brute force computing. But another interesting one, to use a famous economics quote, is thinking fast and slow. So, in control, we like to be thorough, deep, and constrained in our setups, whereas the other side often goes for quick problems, which are at the pace of time, often posed by the current IT companies, say, this is important, we need to solve these LLM problems. And I feel also there we are at opposite end of the spectrum, sort of thorough versus agile research, and obviously we should meet in the middle. And that's where we can learn a lot from each other.
I like to give the example. So I have when I moved to Berkeley, I was in both computer science and statistics. I was neither. I knew some control theory. I knew no statistics, but I had students in both of these two disciplines, and so we kind of taught each other together. And I would sometimes throw out a brand new problem to work on. Do my best to make it sound very hard and very exciting, and then a week later bring them back in and see what they'd say. The computer scientists would come in and they say, "Oh yeah, I figured it out. I wrote it up. It's working. Here's some examples and all that." And the statistics student would come back and say, "I have a proof that it can't work."
Yeah.
So yeah, control theory is not quite that, but I mean there is a little bit of. So statistics did that just because they started getting into problems involving things like, should lead be in gasoline? If lead's in gasoline, the oil companies are happier. There's more efficiency, but medically it can hurt people. It's a quantitative question. If you make the wrong decision, you're going to kill people. A lot of the machine learning stuff has been done with, is there a bunny in the image or not? They've not actually reached this. ChatGPT, not clear. Yes, people complain about fairness issues and all that, but it's really not killed people yet. At least it's not clear. Whereas all these other older disciplines have killed lots of people and saved lots of lives. And so there's a little more cautionary note. I keep saying, I'm really angry right now at Sam Altman and Musk and all these guys. They've taken this to the hilt. Let's just throw it out there, or Zuckerberg, and mess up things and all that. And that's just such vastly irresponsible use of our resources. And they're getting all the young people excited, and it's really, really a shame. And so I think as academics, we need to kind of stand up and say, no, those guys don't know what they're talking about, first of all. Elon Musk knows no computer science or no control theory. And what they're saying is actually harmful. It's not going to hurt people to do things this way. You got to, but you know, but then our fields have got to kind of step forward a little bit and be willing to engage with them, and be a little bit more proactive and try things out and so on, and meet them halfway. But right now we have these kind of, you know, we write our academic papers on Banach spaces, and Elon Musk makes trillions of dollars, and we have nothing in between.
And I think that the sort of the challenge is not just in our field, because again, you know, everything is interdisciplinary, or the problems of the world are infinite, and so. And the disciplinary organization is also somewhat problematic, you know. So I know this and I'm this, and so how do I do it given that I'm a control theorist? And I say, okay, that's the starting point, being a control theorist, and then you gotta decide what you're gonna do in life, and that as a result, you know, you may branch and learn new things and embed yourself in an application and so forth. This is one of the problems we faced in launching IDSS, is that one is that computer scientists were you know, quite arrogant. I mean, the idea is that you just give me data to crunch on. Just give me data to crunch on. That was
These are MIT computers.
Oh, no, no, I don't think so. It was just part of the field. Give me data. I don't care where it comes from. I'll just crunch on it. And then I have social scientists in the room who are saying, how can you crunch on it? You don't even know where this data came from. You didn't do the survey yourself. And it's like, both of you are wrong, right? I mean, you know, so you have to accept the fact that not all your data is going to come from a survey you designed carefully, because there's just a ton of data out there, social data, people's behavior and so forth. You got to figure out something of how to get there. And you can't just crunch on data without understanding where this data comes from. So this overlap is critical, and it is rigor, okay. But it shouldn't be limiting, okay? Rigor shouldn't be, I would not get out of my little boundary because I cannot prove a theorem or something like that. But you always have to remember that rigor is critical when you are trying to help a field develop and so forth. So that's one point I wanted to make about this, is that this idea of coming closer to other fields and understanding their language. So what does that mean for you as rising researchers, and also for your students and our students? I think we have to educate deep and broad at the same time. You know, I mean, I remember when I arrived to MIT as a young faculty, I was chatting with Sanjoy Mitter, my mentor, and he told me, you know, here at LIDS, Laboratory for Information and Decision Systems, every faculty can teach any course that is in the information and system theory area. And so that meant that I had to sit in Bob Gallagher's course in information theory. I had to sit in nonlinear dynamics. I mean, I knew something about that. I knew the controls. I did the signal processing classes. I did the communication classes. In that world, within a year and a half, I literally educated myself so that I can interact and teach any course that was required from me. Now I'm saying we also have to learn basic economics, social reasoning, how to, you know, think about how social scientists think. If you are interested in biology, you got to take some fundamental biology courses. In other words, you have to expand and begin to speak that language. And I would say, you know, at the Broad, we have bi-weekly meetings to talk about how different fields can impact the Broad. And I would say I love those meetings organized by Caroline Euler, my colleague. And the first couple of months, I'm like sitting there, it says, when you guys say state, what do you actually mean? And I get 7-8 different answers.
Connecticut.
I say, I have a definition of a state, you know, from my field, but what do you mean by a state? You know, just getting our language sorted out so that we can actually communicate and work. It's really important for also the transfer of knowledge, because otherwise we speak over each other and we're not going to be helping us and them.
I have an MIT story, which is I first went there as a young professor, and I had a terrible American background, and you know, no math, no control, no nothing. I had done a little control theory, so I started taking classes every semester. I sat in on a class, and I was very embarrassed. You know, I didn't want anyone to see this avowedly knowledgeable MIT professor sitting in these undergraduate classes. And one of the classes was on differential geometry, and it was undergrad, but it was pretty advanced. It was pretty cool. So anyway, I'm sitting there, and I'm hoping no one sees me. I turn around, there's this there's this professor sitting there with Sandro Emitter. Now this guy, he's like 60 and he knows a lot.
Yeah.
But, and he's sitting in an undergraduate class of differential geometry, and you can see his eyes brightening up.
Yeah. Yeah.
So anyway, young people in the room, your education never ends. It starts when you get your PhD. And then every year you should learn something brand new and then put it all together and talk the language of multiple people. A lot of this is about just communication barriers and breaking them down and saying, oh, that's what you mean, and then working with each other.
That's the real luxury of the academic life, isn't it?
It is.
Yes,
It
yes,
is.
yes.
Be able to learn
Yes.
continuously.
It is, yeah.
And we should defend that.
We should defend that. We should defend the academic institution, because the academic institution is under the attack. And what Mike said, the big billionaires are actually undermining the importance of this critical thinking, questioning things, and you're wasting your time, and the world is moving in a different direction. It all started in academia. A lot of stuff was invented in academia. 75 years of development. It didn't just happen yesterday. You have to remember this stuff didn't just happen 2016, 2017. It's been happening, and a lot of development, a lot of sweat, a lot of effort of people that believe in it and do it for the fun and for the development of the field. So let's not forget that and just think, these guys invented the world. I mean,
it's also super international. We're in an era where everybody says that they're doing it. We should, there's all this geopolitical stuff, and it really is about shared knowledge, especially this AI stuff. Look, it's gradient descent. It's on computers we can all get our hands on, right? It's on data, and it's just not the case that Google has all the world's data. I can go out and get some data on the street today that Google doesn't have. It's about data for solving some problem. And you, in your local environment, will get the data for your problem. And then you have all this, and the algorithms are published on the archive. So it's this naivete that we're somehow one country is going to dominate it and all this geopolitical nonsense. That's another level of nonsense. I just can't believe that we are allowing people to talk that way.
And also, I have to say, a benefit that we get from cloud computing and this international so forth is that we can share algorithms, we can share data, and now we can share problems. I mean, you can talk about gene folding, right? I can explain that in my class. I couldn't really do that many years back. Now I can do it, and I can actually run, So this brought problems from different fields closer to us, and the language of statistics and data is allowing us to speak almost the same things when we interact. It's a great time to think about opportunities for what you can do. I mean, I decided not to retire. I'm staying another 10 years.
We're gradually shifting towards the Q&A session. Before we do that, I would like to summarize somehow what did we learn from this hype. If you had to say it in one sentence, one for every panelist.
I'd say we've talked about a lot of different disciplines. In some sense, we're not mathematicians. We all thought we were going to be mathematicians. We all learned a lot of math, and then we aimed to be math wannabes at having these sparkling, beautiful, But math is like Terry Tao. It's like people that really go to the edge of knowledge and then do these abstractions that are, what eventually useful. No, these are fields that are trying to make human life better on this planet in a time of real struggle, and do it in ways that are convincing, trustable, elegant, robust, that the people after us will pick up on them and all that. And so that is an amazing human effort. I think of it as engineering. So whatever you want to call this new field, I think it is an engineering field. It's building things. It's like the civil engineers of the past. They built bridges that didn't fall down. Mechanical engineers, the electrical engineers. And so we're in this new era where it's an information engineering, whatever you want to call it. And we could make things worse for human life, or we could make them better. And so we shouldn't get too obsessed about all the boundaries and all that. And we should, do some math and all that, but really think about it. We have big responsibilities. And so part of all the discussion here has been about what are those responsibilities and how do we connect ourselves to them intellectually.
Rodolphe?
I think we live in a marvelous time to do what we are doing, and so we often think that control is at the end and that it's a dying field. I think it's just an extremely novel field, as well as machine learning and all these area of information engineering that has been booming in the last 20 years.
Florian?
Well, one thing is we all agree on is sort of to break the disciplinary boundaries, especially when it comes to educating young researchers or students in general. and integrate more, I guess, modern elements from, for instance, from computer science. Let it be algorithmic thinking, computation, statistics, just to broaden everybody's horizon.
Munther?
I would say, we should celebrate the decline and death of old models and old ideas, and be courageous to take on the new problems, and not be afraid, to just jump in and think systematically and mathematically and in engineering way to solve real societal problems.
This is wonderful. And with this, we open the Q&A session. So please raise your hand if you want to ask any questions. Don't be shy. Really? Yes.
Towards Professor Jordan on the really popular course you helped. So, a question towards Professor Jordan about the course you helped create. You mentioned that you teach students in such a manner that after they graduate, they are ready to solve real-world problems, but maybe not write papers. So, how would you go on to teach somebody to write papers?
Oh, thanks. That's a fantastically excellent question. This happened to me like 5 or 10 years ago. Someone said, you should help design an undergraduate curriculum. And I thought, no, that's the last thing I want to do. I like teaching graduate students because they're all motivated. I know where they start. I know how to get to the next level. But I think it was a fantastically interesting challenge. And it did lead to people that could do things like get a bootstrap error bar and then do a synthetic control, and these things that I thought about as the most advanced technology we have. That at the end of grad school you might learn about synthetic controls, or about bootstrap at scale, or about conformal methods, blah blah blah. But those are actually turned out to be very easy ideas and very powerful. So why don't we bring them all the way up to the front, teach you that. And then as you start to learn them, for example, I explained the permutation test a minute ago. It needed exchangeability. So it needed an idea, some things that there was an invariance. And so that's group theory. So you hinted at some group theory. Then some probability theory came in. And so by the 3rd or 4th year, now you start to do the math. And you work up towards be able to do something like optimal transport or HJB equations or something like that. So I just kind of want to flip it around. Take the really powerful new ideas and don't start with the old places that we started. But anyway, long story short, I can't really answer your question because I kind of ended after 4-year education. I kind of got to where I felt they're ready to go out in the real world, and they know some techniques that they're going to surprise people out there at Amazon and Google and all that, because none of the older people know these things, but they're immediately what they need to solve the problem. And I'll be proud of that. But now, suppose you want to stay in grad school. I don't know. And so maybe other people can help to answer that. I think it's kind of a fool's errand right now to try to design a graduate curriculum. It's really, each person should be thinking about what piece of this to bring together with other pieces of this, and how to get enough education in that piece. Go on YouTube and watch Terry Tao's blog or whatever. Find new places to get knowledge, and don't just stick yourself inside of one of the classical curricula. But that's kind of back on the individual. I don't really know. As professors, I'm suspicious that we don't know how to do this yet. And maybe one thing just to say is modules. I don't want a whole class a year on linear programming, but I want 3 weeks on linear programming. Duality. I want various pieces. So, but I don't have better ideas at the graduate level.
Any other question?
So to all of you, so it came up a few times, but how could this new control course, this introduction to control course, how could this look like? Like, how do you motivate the students of the future?
I think that this is actually a great question about the future of education, not just about control. The truth is that we're still in this archaic style of delivering data in the classroom. That's all what we're doing. We're not teaching. We're not interacting. We're just basically, I got stuff and I will write it on the board, or I have it on slides and so forth. And since the data is available and you can even have a person deliver it to you online and so forth, I think the classroom should be very different and should be driven by challenges and questions, and then a lot of the techniques. Of course, you need foundations and you need to go through do the foundations. But beyond foundations is not, don't take 8 years. I mean, you don't need that. You can get foundations and then you can build on them on your own. There's a lot that you can do on your own. But then what is the value of the classroom? The value of the classroom is this sharing of ideas and perspectives and this discussion that then builds on something where then, okay, I see something interesting and coming. You know, I don't think I can do that at MIT yet, but if I go back to teach a graduate course like this and I have my material online, I will walk into class and I won't teach. I won't deliver the same stuff that you can get online. I'll try to get people to discuss and think. And so in control, it could be so many different things. It could be from a challenge in a physical problem into talking about, you know, decision theory from an economics perspective and how that looks. You know, it's so many different things you can actually get people thinking and wondering, you know, how do I actually even model this phenomenon? Do I need to model this phenomenon? Do I stay with the data? It's just so many interesting questions. Yeah, I mean, but that's not how we teach these days, you know, unfortunately.
So we recently went through the exercise at ETH to redesign our bachelor control course. I guess Alberto can talk more about that than I can, probably. But the central ideas was, we saw what people were using later on in industry, which was reinforcement learning, MPC, ADP. So why shouldn't we teach that right away in the undergrad rather than let them afterwards tune the black boxes? So we were turning it around a little bit, and we didn't teach them all the math. We just brought them to the point that they can play with it, because that's what we saw works in computer science. They get very early to the point that they can just code things up and it works, and then they figure out the theory afterwards, as Mike said. I mean, that gets students motivated early on. And then, of course, ideally, motivate them by project-based learning. You know, present some interesting problems to them, like land a rocket or whatever, and let them solve it.
You have any thoughts, Rodolphe?
Someone was asking earlier about like machine learning. What can one learn from that? And someone mentioned it, the test beds and the benchmarks. So that's been a huge part of it. Leo Breiman, you know, the two cultures. He said, all my stat friends are just writing papers. The machine learning people collect large amounts of data. They test things out. They have benchmarks, all that. And I didn't really kind of like it. It was too much competitive, you know. I just wanted to share ideas. I didn't want, but it really had a huge, huge impact. And now if you think about control, you know, it's a little harder. You know, the benchmark is a system that does something. And as you probably all know, like the aero industry, Aero Astro had to do huge numbers of simulations of airplanes, right? And Gunther Stein and others. And logistics systems inside of a company like Amazon, they got huge simulations. And they try all their ideas in simulation before they go over. We don't have so much of that in academia, and I think for this overall field to blossom going forward, it's going to need more of that. Some of them are robots, because kids love to play with robots. But also, I want a broader collection of people. You know, my son loves robots, my daughter doesn't, and there's a gender issue. There's just issues. Some people love that, and other people want to solve healthcare and all that. Well, that's a control problem. How do you make sure good medicine gets it? How do you get people treated in timely ways so they don't die? Yeah. Huge, interesting problems that all humans are interested in. Well, build a simulator. And we have lots of games out there now that do things like this. But if academics maybe can start to invest in doing more of this kind of platforms where you can try out really interesting project ideas that are not just robots and, you know, and gaming and warfare and you know, and so on. So this is going out to a broader audience. I hope I think the people will want to do that. I think it was really important in machine learning. I think that's probably the number one thing other than having the cloud and GPUs available, was having these big data sets.
It's already being done, if I can jump in.
Oh, is it being done? So talk about it a little bit.
Yeah, so that's something that Florian hinted.
Yeah.
Was something that we've done together with Saverio Bolognani and many others.
Yeah.
The course is computational control. Offered at ETH, and the project actually was basically controlling an artificial pancreas, and this is done through an FDA-approved simulator of a pancreas. And the students played with many different methods and trying to figure out what works best. So yeah, I very much resonate with what you just mentioned. Although I am the moderator, so I shouldn't jump in.
No, you should jump in. That's probably the most critical comments made the entire artificial pancreas, artificial economy, artificial climate, you know, blah, 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 and then control that and then open up that for people to use it, even if they don't know much calculus.
Yeah.
This feels like, to me, the biggest message we
and allow other institutions to use it if you can.
Exactly. Open source, that's another thing the machine learning did.
Yeah.
You know.
Yeah.
Any more questions? We have time. Yes.
So I want to repeat something that somebody said to me a little bit provocatively, maybe, and just get some reactions. It kind of relates to the evolution of the field that we've heard a bit about, really interesting discussions. And I'm a little nervous saying this sitting next to Anders. What was said was that the days in which like the major advances in designing kind of control and autonomous systems come from proving difficult theorems in linear algebra are over. So that was what somebody said. Do you agree with that? Is the style of research that we need evolving? Is it moving to a more kind of empirical style of research, which we see in some of these other fields? Or what is the role of rigor, I guess, in the future of our field?
I don't hope we never came across saying the end of linear algebra and the end of theory. It's just wrong. We're talking about hundreds of thousands of people. There should be a fraction who are doing yet more interesting linear algebra, maybe in various regimes and limits. He referred to high-dimensional statistics earlier. Well, high-dimensional statistics was done almost all in linear regression first. Okay, but it's linear regression where the number of dimensions is much, much higher than the number of data points. Thought impossible in the past. How could you possibly do that? Well, it's linear regression. It's got to invert some matrix. Oops, I got problems there. So what you do is you have these restrictive eigenvalue conditions. It's yet more linear algebra. And it's yet more constrained. It's the anti going from non-parametric to parametric. This is hyper-parametric. Parametric plus yet more assumptions. And wonderful new ideas came out of all that. And some of them actually had some real math. There was actually some mathematical discovery in some of those, David Donahoe and so on. So it's not the end of linear algebra at all. It just depends on what regime you're working on and what limits you're taking and whether you're doing it non-parametrically or not, and so on and so forth. But if everybody's doing that, then the field doesn't go anywhere. But there's got to be a few people doing it.
There's some data on your question, right? There's this 2018 IFAC survey where they went out to industry and asked them, what are these modern control methods are you really using? And the top three, I guess you can guess them, PID, Kalman filtering, and MPC. Meaning, did we really contribute that much in the past decade? Questionable, right? But at least by that survey, I wouldn't know. I mean, when I work on applied problems, I have another set of research where I work on applied problems in electronics and energy systems. I really flip my mindset and say, no, I wanna solve this problem. I drop my theory standards. Go after the problem. The method doesn't matter.
I think that the future problems aren't just going to be a PID or it's just going to be a whole different world. You can't limit yourself by saying this won't work or this will work, And I don't know what next branch of mathematics, maybe category theory, we were just talking about that the other day. Could be the thing, linear algebra. I mean, just one of my colleagues at MIT, a couple of my colleagues at MIT had this whole idea of how to think about the trade-offs between computation and statistics. And their whole benchmark is what's called the hidden clique problem. So you have a complicated random graph, and you hide a clique in there, and you ask yourself the question, can I find it, right? And if you think about that problem, it's really a matrix problem, right? And the discovery in there is about, well, what size of a clique is impossible to find, and what size of a clique is easy to find, and what's the stuff in the middle, and how we characterize all of this. It's a matrix computation problem. And this is just a few years back. So to say that linear algebra is no longer going to be the core for a new discovery is utterly wrong. And it's just like an unnecessary prediction, right? Why would you do that, Could there be other mathematics that come into the picture? Of course. That's why we have to keep our minds open. But I don't subscribe to these predictions. Nor the predictions, by the way, of what Rodolphe mentioned earlier of, this field is dead and this field is alive and so forth. I mean, we've been in a dead field since the day I entered, and so for some reason, I haven't felt it, and it's been vibrant and so forth. So these predictions are useless.
Yeah. Statistics, same thing. It's been dead since I entered. And if you go out and look at what real people do in real statistics, it's analysis of variance and linear regression. Yeah. 99% of the time. But the devil's in the details. When you're really consulting, you just do it off the shelf, it ain't going to work. You got to do a little bit of robustness. You got to shape your variables. You got to do this and that. You got to put it together with you have your thinking hat on. And if you do that together, and then that'll sometimes inspire a cool new math that you didn't know about.
I also hope and believe that a lot of what has been done in the last 10 years in the field will not show up in surveys before 20 years.
That's true.
And that's
Yeah,
great.
sure.
That's true.
I think we have time for one last quick question.
This question is not directed to anyone specific, but I assume you have students that go out to the real world and solve problems that make, as Micheal put it, make human lives better. So what feedback do you get from these students? Do you get some opinions that are like, oh no, we never use that, we use this, we use that? Or what are your thoughts on that?
I mean, I think we as academics, it's our responsibility to make sure we're in contact with that all the time, that kind of dialogue all the time. It doesn't, you know, it's just absolutely my responsibility to know what's really being done out there. And I think I have a pretty good grasp of it. I spent a day a week at Amazon partially, but also I will grab students and all and find out. And long story short, it doesn't surprise me mostly. Hedge fund people claim they're doing something brand new that no one ever talked about and all that because they can't tell you their secrets. But if you give them enough sake or whatever it is they drink, they'll tell you, and it's MPC or you know or Bootstrap or you know it's something we know about. But yeah, it's absolutely critical to academics cannot just be doing the academic thing. They got to have and they don't just, consulting can be a fantastically interesting thing to do. Go in, really learn about the problem, try to help them solve it, and then keep going.
So one thing I would say, a different dimension to that answer, and this is specific to me, each person supervises students differently. I never really give my students problems to work on. I never tell them what to work on. And it's a hard thing for me to guarantee the funding for this particular game, but I think it's finding the problem and what you want to work on, I think is a huge part of your PhD thesis. And so you find the problem, you jump into a field which is complex and has so many papers and so many things and experiences, and they read about what the technologies are and so forth, and then they got to formulate something interesting and solve it, right? And that exercise, to them, with the feedback I get from them when they go out to industry, not the academics, because it's a little bit of a different game, they feel so empowered that they did this, that they are able to see through a lot of crap in front of them and then get to the bottom of the problem and solve the problem. And I think that also comes with the rigorous training and the critical thinking and isolating the issue. Not getting overwhelmed with all the details that are coming around. And they do very well that way, and that's the feedback I get, and I get happy about that because that was the intention of that particular style. So, and that's what I would emphasize, is that you really have to kind of, you all look to me like students, by the way, so I'm sorry if you're already professors. But, to think about that as well as in your career.
Yeah, I want to echo that. We have actually a name for that in our group. We call it the power of abstraction, because that's what people really are good at when they go out into industry and like all the messy problems. They can put structure into that, and due to training, they can figure out a solution. Whereas for other people, it just always remains a complex problem. And I guess that's what your training really enables to, see the world in a block diagram or however you want to put it.
Bob Gallagher, one of my colleagues, information theorist, an amazing guy, always objected, to echo Florian's comment, to anything that is called complex center, complex this. It's like his idea is that that's the stupidest thing you can do. We don't embrace complexity, we break it, And I always thought that was this really interesting thing, is that, part of what we do is maybe embrace it by breaking it and putting it all back together. But it is important to see the nuggets and the core difficult things. Not everything in the complex problem is really complex. There's a lot of red herrings there. But there are a few things that are really hard, and you want to get to the bottom of it and solve the hard problems. It's not always obvious. Sometimes you miss, but that's kind of part of the exercise.
Here I have to jump in because unfortunately we really have to wrap up. It's been a wonderful journey for me. Let's thank our speakers. So I hope we learned something from the hype. If not, please continue the conversation on social media. I take this opportunity also to announce that we are launching the inControl shop, so t-shirts or hoodies or mugs with this brand will be available to you. Check that out on social media. Thank you so much for staying with us.
Thank you.